So let's start with the main topic then, that is choice of optimum blade loading. So initially, the first set of examples that we are going to look at will be related to subsonic impellers. And generally, we find in subsonic impellers, the dominant source of loss is secondary flows. And so the type of loading that we specify has to control these secondary flows. So the first example that we are going to look at is an industrial compressor, which is a typical compressor stage, which is used for multi-stage centrifugal compressors. And we have some information about the specs over here. So the tip diameter, flow coefficient, the tip speed Mach number, and the number of blades. And essentially, there is a vaneless diffuser here. Then this is coupled with a return channel. And generally, we then use this in a multi-stage environment. And what we are actually going to look at here is the isolated impeller in this presentation. So what we are seeing here is the actual flow field that was predicted for the conventional impeller. And what you can clearly see with these streamlines is that were created very close to the blade suction surface, is that there are strong secondary flows moving the low momentum fluid that is generated on the suction surface from the hub towards the shroud trailing edge region. And you can see how these low momentum fluids in the boundary layer are being moved by the secondary flows, and then they result in the formation of this exit flow non-uniformity at the exit of the impeller. In fact, this non-uniformity at the exit can result in high mixing losses and then high diffuser and stage losses, and also it can contribute to compressor instability, at least in the case of vane diffusers. So in fact, one of the major sources of loss for many industrial applications, at least for subsonic impellers. For transonic impellers, as we'll see later, shock losses become the more dominant source of loss, but here it would be secondary flows. And so what we want to do is then to look at how we can actually reduce this exit flow non-uniformity. Now, the expression for the generation of secondary flows in rotating channels was derived quite a while ago. And here W is the velocity, omega is the absolute vorticity, and so W dot vorticity is actually the streamwise vorticity. So what this shows is that streamwise vorticity will be generated along the streamline if you have a component of vorticity in the direction of streamline curvature acceleration, or in the direction of the Coriolis acceleration. And then based on this, you can divide the rotating channel into these three parts. But generally in the inducer region here, we don't get a lot of secondary flows because the boundary layer hasn't grown very much. And also in the radial section, it's mainly the tangential component of Coriolis acceleration. But when you come to section 2, which is the axial to radial bend, here you will have two contributions. And in fact, this component will actually result in secondary flows on the hub from the pressure to the suction surface. And then these then finally get moved up along the suction surface and then are dumped near the trailing edge. And so what this equation shows then is that in section 2, you can get very complex secondary flow patterns moving the low momentum fluids both at the end walls and the blade surfaces, and then moving all these losses to the tip trailing edge plane. And then in fact, you can use the momentum equation and express the Coriolis and streamwise curvature accelerations in terms of gradients of reduced static pressure. And this is for incompressible flow, whereas for compressible flow, this will be enthalpy. And in fact, you can show that secondary flows are generated whenever there is a gradient of reduced static pressure or relative Mach number in the case of compressible flows in the direction of vorticity in the flow field. And then this is actually a very easy way to look at the problem and then solve the issue. Now, if you look at the relative Mach number on the conventional impeller, what you see is that what's essentially driving the secondary flows is this difference between the pressure and the suction surfaces, which is critical. So the difference in the relative Mach number between the suction surface of the shroud and the suction surface of the hub. And if you can reduce this gap, then we should be able to reduce the secondary flows. And in the inverse design method, we actually control the pressure jump across the blade. So we actually control the blade loading here. And so this is the gap that we directly control. So by making changes to blade loading, we could very easily adjust the overall surface Mach number in such a way that we can reduce this gap, as we show here in this example. And this should then help to reduce secondary flows in the impeller. So in fact, the type of loading that we use, and in fact, this also works for pumps, which we showed in our previous webinar on pumps, is a fore-loaded distribution at the shroud and an aft-loaded distribution at the hub. And the net effect of this type of change is that essentially it will help you to raise the suction surface hub velocity and reduce the suction surface shroud velocity, and therefore reduce this gap, which is essentially what we're trying to achieve here. And so this is actually the key element of this approach. And so let's look at this example of a case where this type of compressor was actually designed. And in fact, it was a redesign of the case that we saw earlier. And now you can clearly see the reduction of the secondary flows on the suction surface, resulting in a much more uniform flow at the exit. And in fact, what you see here is the test results from the same test facility that we saw earlier. So basically the impeller, the vaneless diffuser, and the return channel. And then what we are seeing here is the stage results using the total pressure and temperature at the inlet of the impeller and the exit of the return channel. And then using that data, what you see is that a 5-point improvement in efficiency could be achieved. So the key is that when you get a more uniform exit flow, you don't just benefit the impeller, but you benefit the stage as a whole, because your mixing losses are then reduced. And here you can see the blade angle differences between the conventional and the inverse impeller. And clearly there's a substantial change, and a lot of conventionally designed impellers have very similar blades to what you see here. And also you can see the resulting blade angles here are very, very different. And actually this is probably one of the reasons why, perhaps, even though the nature of secondary flows was well understood for many years, it was very difficult with conventional approaches to try and suppress secondary flows in a systematic way in the impeller. So let's come to the second case, and this is actually a subsonic compressor, but this time it actually has a splitter as well. So, but in fact, what we'll soon find out is that its treatment will be very similar to what we did for the first case with full blades only. So this particular case would be actually higher tip speed Mach numbers, around 0.85, 0.9. And this was in fact a collaboration with ETH Zurich, Sulzer Turbo, and ABB Turbo. And one of the advantages of using inverse design is that when you have a splitter blade, you can actually adjust the loading on the splitter and the full blade independently. And then the program automatically finds the optimum pitch-wise location of the splitter. And this is actually quite an important advantage in the splitter design. And so what you see here is basically the loading distribution that was prescribed. So it's fore-loaded at the shroud and aft-loaded at the hub. And the difference is that the black lines here, they represent the full blade, while the red lines actually represent the splitter. And so you can see both the splitter and the full blade have the same distribution, that is fore-loaded at the shroud and aft-loaded at the hub. And this type of loading then gives this type of a blade shape. And then what's quite interesting here is that when we are looking at a comparison of the blade angles, and the open triangles are actually the conventional blade angles. And of course, in conventional design, the blade angles are actually the same between the full blade and the splitter. But in the inverse design, there's about a 5-degree difference between the splitter and the full blade. The difference is actually much smaller at the hub, both between the splitter and the full blade, and even between the conventional and the inverse designs. And this is probably because the conventional impeller was aft-loaded both at the hub and shroud, while we are fore-loaded at the shroud and aft-loaded at the hub. So one of the nice facilities they had was the ability to do fast response probe measurements. So then what you can see here is the measurements of the exit flow non-uniformity from the impeller. And so the lower is the conventional design and the upper is the inverse impeller. And this is actually the relative velocity measured with this fast response probe. And you can clearly see that there are quite big non-uniformities in the conventional impeller, especially between this channel between the splitter suction surface and the full bed pressure surface. And there is a strong variation both in span-wise as well as the pitch-wise directions, while in the inverse impeller, there is much less pitch-wise and span-wise variation as a result of a better control of secondary flows. And this shows you the total pressure measurement data. And again, you can clearly see a region of accumulation of low momentum fluid around the suction surface here. And this is something that's actually been eliminated from the inverse impeller. Also, using the probe measurements, it was possible to measure the efficiency at the exit of the impeller, which is shown in red here. And there was about 2 points improvement in the efficiency at the impeller exit. And then for the mixed out conditions at the stage exit, there was in fact a 5 to 6 points improvement. And this means that by making the impeller more uniform, you can actually get quite substantial improvements in the efficiency as a result of a reduction in mixing losses at the impeller exit. So some concluding remarks on subsonic impellers. So basically, generally for subsonic impellers, whether full-bladed or splitters, we tend to use an optimum loading distribution, which is fore-loaded at the shroud, aft-loaded at the hub. By using 3D inverse design method, it's then very easy to design impellers with this type of loading, and it results in better control of secondary flow and more uniform exit flow from the impeller. And of course, as the experimental results have confirmed, more uniform impeller exit flow results in significant reduction in mixing losses and an increase in the stage efficiency.